Hi, my name's Matthew. We are our team Design Devils, and for our project, we decided to do farm bots. And my portion of the assignment is going to be covering a irrigation bot.
Hi, my name is Matthew. I created and worked on the crop progress robot for our project here.
Hi, I'm Brandon Jameson, and I worked on the analyzing bot for our project.
I'm William Brock, and I did the harvesting bot for our project.
I am William Brock, and I am presenting the introduction slide for the Design Devils. In this slide, we have the history and kind of some facts about what the reason why we chose the designs that we chose. You have an outline of all the slides that we'll be talking about and the order that they will be received, and the design requirements for all of our robots. I'm William Brock, and this is my CAD design for the harvester bot. I like to point out the dimensions here in this corner in the top left. The grabber claw, it has a plow as well as a basket to store the potatoes, and it has drive tracks to move to different locations. This is the circuit design. I'll go through a simulation in a few minutes. The drive operations flowchart. Basically, the simple version is anything inside of 6 inches, it will not turn in those directions. Anything outside of 6 inches, it will allow it to turn in those directions using the front as the first, and the condition that all of them are less than 6 inches will go into an all stop situation. The code for the drive operation, the grabber operation flow chart. Max range is 16 inches, so anything outside of 16 inches it won't be able to grab. Anything inside of 16 inches, it will begin to sort plants, objects, and potatoes. This is the code for the grabber operation. This is the simulation of the drive operation and the grabber claw operation. I'll start with the right sensor here. Once I move it past the 6-inch mark, it'll display the right and left distances, so that way it can determine what the distance is, and you'll notice that the gears are moving here. If I bring it in and I switch to a different sensor and move this one out, it'll begin to move in the back distance, and you'll notice that these are in negative RPMs. Switching to the grabber claw operation, I have it set so that way it starts in the out of range distance, and it'll show that it's out of range here. I'll move it in, and you'll notice that the servos, once I get past 16, they'll start to rotate, and it'll give the angles here as well as the distance. If I move it over here, or move it over here, the servos will change to meet those demands and rotate the angles. This concludes my presentation. Thank you.
Hi again, it's Matthew. Today we're going to be looking at the mechanical design for my crop progression robot, or data collection robot more accurately. You're going to see that it's encased in an aluminum shell. It has heavy-duty wheels. It has a few actuators and sensors, and then some motors as well here on the back. These are going to be distance sensors, and these are going to be temperature sensors. And then these are some of the internal components that I couldn't show. It's going to rotate this part upwards so that it can calculate the distance. And then when that distance drops off plants in front of it, it's going to be able to calculate how tall they are. This is my circuit design. We're going to talk about this a little bit later, but essentially this is going to propel and rotate the tires. This is going to check the distance in front and work with this. This is going to calculate the plant's height, and then this is going to calculate the temperature. This is the flowchart slide for the logic. Obviously, it's going to start here. It's going to have a user hub. This hub is going to determine what the robot does. If it chooses that needs the robot to drive somewhere, the robot will drive, avoid obstacles, redirect when necessary, decide if it's at the location, and then retrieve a temperature and plant height. Okay, so this is the Arduino code that goes along with that logic structure, and we'll see more of this on the next slide when we see it simulated.
I'm going to be looking at the circuitry for my proposed robot. This is the code. Let's go ahead and start a simulation. If we look over here, they're broken down into 3 cases. Case 1 is the motor. When the motor is called, the motor will go forward. You can see that right here. Changing the distance. If it sees an object in its way, it will immediately turn the wheels, stop, and go backwards. When the distance is further away from the object, it will go forward again. Our second case is our temperature sensor. You can see right here, changing the temperature, sets out different outputs on the monitor right there, which will be delivered to our central hub in a actual Fahrenheit degrees format. And then case 3 is plant height. So if we go ahead and call that, so say we get close to a plant, it'd be within 5 inches of that plant. What will happen is this motor right here will rotate and cause this sensor to go higher and higher. As long as it reads within 5 inches that the plant is there, it will count. Per inch it goes up, and then when the plant is further away, say it reaches the top, it will print out to the screen how tall the plant is, which would be great for farmers, so they don't have to go inspect their fields.
Welcome back. I will be covering our irrigation bot. So our irrigation bot is a double wheel rotary ditcher. The components of this ditcher include, starting from the front, a distance sensor, and then in the middle a DC motor. Behind that is an A-frame that has a hydraulic lift that lifts the ditcher, and on the ditcher is a servo motor and a tilt sensor. And there has been no changes since my proposal. So this is what my Arduino circuit it will look like. It has a Arduino board, 2 small breadboards, a DC motor, a servo motor, a distance sensor, a tilt sensor, and a L293D H-bridge motor driver. And on the right you will see all the code. And there has been no changes since the proposal. Right, so on this slide you'll see the demonstration of the Arduino circuit, and in a second you'll see that the tilt switch is going to be activated, simulating that there's been a tilt, and then you will see the servo motor rotate 90 degrees. Okay. So this is my flow chart for my irrigation bot, the ditcher. So from the start, it will receive a command from Central Hub. If the distance sensed is greater than 5, the bot will move to the designated area that is being called to. If not, it'll stay put. If the ditcher is set between 30 and 40 degrees and the hydraulic lift lowers the ditcher, the tilt sensor will connect and trigger the servo motor. At this point, the job is completed and can return to the start. If either the tilt sensor or servo motor do not connect, the bot will stay in place for further evaluation.
All right, so here we have the mobile robot, which is used to analyze and inspect the crops for any unwanted growth, potential diseases, or pests. And the camera that you see is there to capture any evidence of these potential hazards if it were to occur. And the wheels are tractor-specific design wheels, so the mobile robot is able to handle the same terrain any regular tractor would be able to handle. Here we have the circuit design for the mobile robot. distance sensor connected to the Arduino, so the robot can determine the distance from crops in order to avoid causing any damage to them. Of course, we have 2 gear motors for the wheels specifically to make the robot go forward and backward. And we also have the 9-volt battery connected to the breadboard to give it power. Here is the code for the mobile robot to fulfill its duties on a daily basis. So the flow chart for the mobile robot is very simple. It's just here to analyze, inspect, and report. So as it receives commands from Central Hub, it'll go out and inspect the crops. And if the crops don't meet the standard, it stops and reports the issue to the Central Hub, and it'll carry on with its inspection. If there are no issues, it just goes throughout the whole inspection, and after finishing the inspection, it'll finalize the report and send it off to the Central Hub. Alright, here's our simulation for the mobile robot. And as you can see, it starts off with a turn left, then every 10 seconds, come back with another turn left. So if I were to stop the simulation, go in here and turn right, and start up the simulation again, we would also get the same thing with the distance sensor feeding into the Arduino, going straight to the gear motors, giving it a turn right or a turn left every 10 seconds.
Okay, so now that we've taken a look at how each individual robot will operate, I wanted to give you a view of how the robots will work together. We decided that we wanted it to have a central hub that allowed the robots to go and complete tasks, but have the robots be autonomous on their own. So our central hub will essentially consist of a user asking the robot to complete a specific task. The robot will complete that task, and then it will return after that's completed. And that's the way with all of our robots. And some of our robots will return values, video, or just complete a task.
Entrepreneurial aspects. We estimate that our SwarmBot system would cost around $585,000 to build and place in operation. This is a base price, and depending on the customer's needs, this price could go up. Our SwarmBots are a valuable system that can help farmers cope with the labor shortage.
Alright, to wrap this up, we've learned that in some cases, sometimes less is more. Creativity plays a key role in developing a new item or product. And together we've been able to add to our skill set or learn new skills. And today we've been able to give 4 different outlooks on how we can help the farming industry.